Good day, class. You're welcome to our physics class. And in physics today, we shall be looking at the topic temperature and thermal expansion. Alright, so in this topic, we will look at the meaning of temperature, heat, and thermal expansion. After which we shall solve some questions. So our main focus is to solve questions relating to this particular topic. And so what do we refer to temperature? Temperature is the degree of hotness or coldness of a body. And so when you touch a particular body, you will detect if it is hot or cold. And what do we refer to as heat? Heat is the total internal energy of a body. And the two of them are related. How are they related? When you heat a body, the temperature will increase. And so they are related in that on addition or removal of water from a body, there will be an increase or decrease in its temperature. The quantity of heat is measured with the use of a calorimeter and the unit is in joules, while temperature is measured with the use of thermometer and the unit of temperature are degrees Celsius or Kelvin or degree Fahrenheit. These are the units. Now, talking about thermometers, we have several types of thermometers. These thermometers include the liquid in glass thermometer, we have the bimetallic thermometer, we have the resistance thermometer, we have the gas thermometer, and we also have the thermoelectric thermometer. Talking about the liquid in glass, we have different liquids that could be in there, such as alcohol, mercury, or water. Some of these liquids are better than the other because of the physical characteristics which change in respect to the change in temperature. Now, take note that, like we said, that you can measure the temperature of a body in degrees Celsius, Kelvin, or degree Fahrenheit. So, if you are given a body in degrees Celsius, the SI unit of temperature is in Kelvin. And so, if you are given the temperature of a body in degrees Celsius, you can convert it into Kelvin. And how do you convert it? Temperature in Kelvin is equal to the temperature in Celsius plus 273. We shall look at questions under this. And if you are given a temperature in degrees Celsius and you are required to change it into Fahrenheit, the temperature, the formula that relates Celsius to Fahrenheit is temperature in degrees Celsius over 100 equal to temperature in Fahrenheit minus 32 over 180. And so if you are given your temperature in degrees Celsius, you can convert it into Fahrenheit by using this formula. And if you are given in Kelvin and you have to change it into Fahrenheit, so what you have to do first is to change it into degrees Celsius first. Then from degrees Celsius, you change it into Fahrenheit. Now there are some characteristics of these thermometric liquids that make them suitable. Now if you consider a thermometer, for instance, a liquid in glass thermometer using mercury. If we have a temperature of 0 degrees Celsius and 100 degrees Celsius, for instance, here this 0 degrees Celsius indicates the ice point for water. Ice point for water. Okay, let's take this as a water in glass thermometer, in which 0 degrees Celsius is the ice point and 100 degrees Celsius is the steam point. This ice point can also be referred to as the lower fixed point, while the steam point can be referred to as the upper fixed point. Now, other thermometers have their own calibration, but let's take this as an example. And so, if we say that the distance between here and here is 20 millimeter, so we can assume that here is 0 millimeter and this place is 20 millimeter. So you could be asked several questions based on things like this, such as if you measure the temperature of a body and the temperature rose from 0 to let's say 45 degrees Celsius, what is the corresponding height on the thermometer? Thermal expansion. When we are talking about thermal expansion, we are talking about the fact that bodies, when they are heated or cooled, they have the tendency to expand. When they expand, they increase in size, or they can contract, and when they contract, they decrease in size. They decrease in size whenever they are cooled. So molecules of most solids and liquids expand or increase in size when they are heated or contract when they are cooled. For instance, if you have this as a rod made of iron, this iron could have an initial length of 5 meters. Now, if this iron is heated, the length of the iron tends to increase. And when the length increases and a new measurement is taken, it is possible that it has increased to 5.1 meter. The increase in length is as a result of the temperature, which caused the vibration of the molecules of the iron. And when the temperature is reduced, that is, when the heat is removed, it will return to its original 5 meter. And if it is further cooled, that is, it is cooled beyond the original temperature, there is a possibility of it contracting below 5 meter. When we consider the increase in length of a body, we shall be talking about linear expansivity. So when we talk about linear expansivity, we are talking about the increase in length per unit length for each degree rise in temperature of a body. And linear expansivity is represented with alpha, where alpha is equal to the increase in length over its original length times the change in the temperature. So it could be written as L2 minus L1 over the original length multiplied by temperature 2 minus the original temperature. So here is the formula for linear expansivity. The effects of this linear expansivity are both advantageous and disadvantageous. Some of the applications of this expansion include the creaking noise on the galvanized iron sheet. So during the day, when the weather is hot, the iron sheets will tend to make creaky sounds because they are expanding, that is, increasing in size. And when the weather tends to cool, they will return to their original size because they will be reducing in size. Also, there are gaps that are left between the sections of rail so that they can expand. If these spaces are not left there, it is possible that during the day when the weather is hot, the railroad will expand and can lead to a bulginess in the rail lines, and an oncoming train could get derailed as a result of this. Gaps are also left in metal structures of bridges so as to expand, and then we can use it in the bimetallic strip and also for removing tight stopper by standing the hot bottle in hot water. When we consider a two-dimensional body that has length and breadth, and we consider the increase in length and breadth of this body, we will be talking about another quantity known as area expansivity. In area expansivity, we are required to find the initial area and the final area, also the initial temperature and the final temperature. So the formula for area expansivity, which is beta, is equal to the increase in area divided by the original area times the change in the temperature. So we have it as A2 minus A1 over original area multiplied by T2 minus T1. And also we should not forget that beta equal to 2 of alpha. That is, we get area expansivity from multiplying linear expansivity by 2. Next, we talk about volume or cubic expansivity of a material. So when we talk about a solid body, the volume or cubic expansivity has a sign as this. Now, volume or cubic expansivity is an increase in volume per unit volume for each degree rise in temperature. And we have it as the increase in volume over the original volume times the change in the temperature, which is V2 minus V1 over original volume times the change in the temperature. Take note that volume expansivity can also be gotten by multiplying linear expansivity by 3. And there's a relationship between cubic expansivity and area expansivity. Now we are aware that cubic expansivity equal to 3 times linear expansivity, and we are also aware that area expansivity equal to 2 multiplied by linear expansivity, making Making alpha the subject of formula, we have it as alpha equal to cubic expansivity over 3, and then alpha is also beta over 2. Now we can equate this, since this is alpha and this is alpha. Those are the linear expansivity. When we equate, we have that cubic expansivity over 3 is equal to area expansivity over 2. When we cross multiply it, we end up having 2 of cubic expansivity equal to 3 of area expansivity. So here is a relationship between cubic and alpha expansivity. Alright, so talking about cubic expansivity of liquids. Now in cubic expansivity of liquids, we are saying that liquids expand in volume, quite alright. But the volume of the liquid is present in a particular container, and that container also has the possibility of increasing in volume. Hence, there is a real cubic expansivity of liquid, and there's also an apparent cubic expansivity of the liquid. Now, the real cubic expansivity considers only the expansivity of the liquid, while the apparent cubic expansivity considers the liquid being heated in an expansible vessel. And so there is a link or a relationship between the real cubic expansivity and the apparent cubic expansivity of the liquid, with this formula where this is the real cubic expansivity of the liquid equal to the apparent cubic expansivity of the liquid plus the cubic expansivity of the containing vessel. Let's talk about anomalous expansion of water. Liquids, when they are heated, are expected to expand. So when they are heated, there is an increase in their volume while the mass remains constant. Water as a liquid does not expand uniformly. It expands abnormally, and that's why we have it as anomalous expansion of water. Now this is what we mean. So let's take ice water at minus 10 degrees Celsius, which is being heated. Now as it is being heated, the ice will expand. As it's being heated, it expands till it gets to 0 degrees Celsius, and this 0 degrees Celsius is ice. Here we have ice. Now as it is further being heated, it turns to 0 degrees Celsius of water, and then from 0 degrees Celsius to 4 degrees Celsius of water, and on until it boils at 100 degrees Celsius. From 0 degrees Celsius of ice to 4 degrees Celsius of water, instead of it expanding, it contracts. Now this contract means that it reduces in volume while the mass remains constant. While from 4 degrees Celsius to 100 degrees Celsius, it expands on and on. This is abnormal because we expect it to continue to expand until we have 100 degrees Celsius. While when you are cooling it, the reverse happens. That is, from 100 degrees Celsius to 4 degrees Celsius, it contracts. Then from 4 degrees Celsius of water to 0 degrees Celsius of ice, it expands. And then from 0 degrees Celsius of ice to minus 10 degrees Celsius of ice, it contracts. Now, from this pathway on this board, if we have that the mass is constant, let's take the mass to be 10 kilogram, and then the volume varies. So let's say that initially it was at 5 cm cubed initially. So the density at this temperature is going to be mass over volume. So we'll have 10 over 5, that is 2 kilogram per cm cubed. That will be the density. But as we proceed here, since it contracts, that means the volume will reduce. And so if the volume reduces, let's say that the volume reduced to 2 cm cubed. So we have a new volume of 2 cm cubed over here, meaning there will be a change in the density. And what will happen to the density? Since the mass remains the same, that's 10 over 2, we'll have 5 kilogram per cm cubed. Here it means that there's an increase in the density. And so what we are saying now is that there is a maximum density at 4 degrees Celsius in water. There's a maximum density at 4 degrees Celsius, and afterwards it continues to to expand and the density will decrease. An iron rod has length 50 meter when the temperature is 20 degrees Celsius. By how much will it expand when the temperature rises to 30 degrees Celsius? Linear expansivity equals to 0.0000012 per Kelvin. Alright, so in this question, we're told that the original length of iron is 50 meters and the original temperature is 20 degrees Celsius. Now, by how much will it expand when the temperature rises? So that means there's a new temperature which is 30 degrees Celsius. We're told to find the increase in length. So that is the change in length, which we do not know. And we're told that the linear expansivity is 0.00012 per Kelvin. From here, we have a formula that the linear expansivity is equal to the change in length over the original length times change in temperature. Here we have a linear expansivity and the change in length is unknown. The original length is 50 multiplied by the change in temperature, which is 30 minus 20. And so we have making the change in length the subject of formula, that's 0.00012 times 50 multiplied by 10, and that would give 0.006 meter as the change in length. A glass bottle full of mercury has mass 500 grams. On being heated through 35 degrees Celsius, 2.43 grams of mercury are expelled. Calculate the mass of mercury remaining in the bottle. Cubic expansivity of mercury is 1.8 times 10 raised per minus 4 per Kelvin. Linear expansivity of glass is 8.0 times 10 raised per minus 6 per Kelvin. So let's get this information right. We're told that a glass bottle full of mercury has this mass, meaning that the glass plus the mercury inside it gives a mass of 500 grams, and it was heated through 35 degrees Celsius, meaning that is the change in temperature, which is 35 degrees Celsius. Then 2.43 grams of mercury expelled. That is mercury expelled. Calculate the mass of mercury remaining. So you are looking for mercury remaining, taking the cubic expansivity to be 1.8 and the rest. In this question, we are to find the mercury remaining. Now, the glass is an expansible glass. We are going to consider the cubic expansivity of the vessel which is containing the mercury. So from here, we're told that linear expansivity of glass is equal to 8.0 times 10 to the power of minus 6 per Kelvin. Therefore, considering the cubic expansivity of glass, which will be 3 times alpha, and that is 3 times 8.0 times 10 per minus 8, and that will leave us with 24 times 10 raised per minus 6 per Kelvin. So here is the cubic expansivity of the glass. Next, we're given the real cubic expansivity. Now, the cubic expansivity we're given there is the real cubic expansivity. That is the expansivity of the mercury, just the mercury. So we're given the real cubic expansivity of the mercury to be 1.8 times 10 to the power of minus 4 per Kelvin. And we are looking for the apparent cubic expansivity. Why? Because this particular mercury was heated in an expansible vessel, and we have a formula that says that the apparent cubic expansivity is equal to real cubic expansivity minus the cubic expansivity of the vessel containing the mercury. All right, so this is the apparent cubic expansivity, and apparent cubic expansivity means the increase in volume per unit volume per degree rise in temperature of the mercury when heated in an expansible vessel, but this one only gives us that of just the mercury. All right, so we've gotten the cubic expansivity to be this, and so we'll derive our apparent cubic expansivity from here by having 1.8 times 10 to the power minus 4 is the same thing as 0.00018 minus the cubic expansivity of just the glass. Now this of just the glass is the same thing as 0.00024, and when we subtract this, we'll be left with 0.000156. So here is the apparent cubic expansivity. Now there's a formula that relates this, where the apparent cubic expansivity equal to mass of liquid expelled over mass of liquid left times the temperature rise. This formula is basically for apparent cubic expansivity. There is another formula that still has this, whereby we will talk about volume of liquid expelled over volume of liquid left times change in temperature. So it depends on the parameter we're given. If we're given volume, we use volume. If it is mass, we use mass. The apparent cubic expansivity, which is what we've gotten here, that is 0.000156 equal to mass of liquid expelled. We're giving that to be 2.43 over mass of liquid left. That is what we are looking for. So we represent that with x times change in temperature, which is 35 degrees. We will have a cross multiplication whereby we have 0.000156 times x times 35 equal to 2.43. Making x the subject, we'll have 2.43 divided by 0.000156 times 35, and so we'll be left with 445.05 gram. So here is the mass of mercury remaining after it was heated. We could actually calculate the entire mass of mercury that was inside the glass by saying 445.05 plus 2.43 gram, and that would be 447.48 gram. So this is the total mass of mercury that was inside the container, but this is the final answer which we are looking for. Alright, so in this next question, we're told that a rod of iron and a rod of zinc are each 2 meters long at 0 degrees Celsius, and both are heated equally. At 50 degrees Celsius, the zinc rod is found to be longer by 0.181 centimeter. Find the linear expansivity of iron when that of zinc is 0.0000598 per Kelvin. Alright, so first, we're told that the initial length of iron is 2 meters and the initial length of the zinc is also 2 meters. The initial temperature of iron is 0 degrees Celsius. The initial temperature of zinc is also 0 degrees Celsius. Now, the change in temperature of both of them is 50 degrees Celsius. Now, it was found that at 50 degrees Celsius, the zinc rod is found to be longer by 0.18. So if we put up a diagram of such, we take this as iron and we take this as zinc. So let's say initially both of them had this length, and so zinc has expanded beyond iron by 0.181 centimeter, but we do not know the expansion rate of iron and we do not know the exact expansion rate of zinc, but we know that zinc will be x plus 0.181. That's how we get the expansion of that. So in this question, what we'll do is use what we're given. We're told that zinc has a linear expansivity of 0.0000598 per Kelvin. So let's use what we're given here. We have linear expansivity of zinc is equal to the change in length, which we do not know, but we know the original length of zinc. All right, and we know the change in temperature. So first, let us get the change in length. That is the entire change in length for zinc, which we will call it y. And when we have gotten that, we will take our next step. So the linear expansivity of zinc from the question is this. That's 0.0000598, and then the change in length, which is unknown, over the initial length of the zinc, that is 2, multiplied by the change in temperature, that is 50. Looking for change in length now, we will have it as 0.000059 times 100, and that will leave us with 0.00598 meter as the change in length for zinc. And the change in length for zinc is from its original length, which is 2 here, until it has expanded up to here. Alright, meaning that from here to here, which is the expansion rate for zinc, so that is our y, that's 0.00598 meter. And we are told that zinc expanded 0.181 centimeter more than iron. So for us to get this x, is going to be the full minus, that's the full expansion of zinc minus the extra. So that will be x will be y minus 0.181 centimeter. Take note that we are giving this in centimeter, so we have to convert it into meter so that we'll have the values to correlate. So we have our y to be 0.00598 meter minus, changing this one to meter, will be to divide by 100. So we have 0.00181. And so when we subtract this, we'll be left with 0.00417 meter. So this is the expansion, the change in length for iron. Well, to calculate the linear expansivity of iron, and so the linear expansivity of iron, that's equal to the change in length over its original length times the change in temperature. The change in length is 0.00417 divided by its original length, which is 2, times the change in temperature, which is 50 degrees Celsius. And when we multiply this, we'll be left with 0.0000417 per Kelvin as the linear expansivity of iron. This next question says that a cube with side 100 centimeter at 0 degrees Celsius is heated to 100 degrees Celsius. If the sides become 100 centimeter long, find the linear expansivity and the cubic expansivity of the material of which the cube is made. We have the original length as 100 centimeter. We have the final length to be 101 centimeter. So let's change this into meter. It will be 100 divided by 100, that is 1 meter, and here will be 1.01 meter. Then we are told that there's a temperature change, that is the temperature change is 100 degrees Celsius. So let's find our linear expansivity first by saying the change in length, that is L2 minus L1 over original length times the change in the temperature. So we have 1.01 minus 1 over original length, which is 1, into bracket 100. So we left with 0.01 over 100, and that will leave us with 0.0001 per Kelvin. That is the linear expansivity of the material. Then we are told to find the cubic expansivity of the material, and we are aware that the cubic expansivity of the material equal to 3 times the linear expansivity. So we have it as 3 multiplied by 0.001, and that is 0.003 per Kelvin. So that is the linear expansivity of the material. This question says two metals P and Q of lengths 11 and 12 are heated through the same temperature difference. If the ratio of the linear expansivities of P to Q is 2:3 and the ratio of their length is 3:4, what is the ratio of increase in length of P to Q? This is simple. The only thing is, let's take the information one after the other. So we have two metals, P and Q. Now we're told that the length of P is 11, the length of Q is 12. And we're also told that the ratio of their length is also 3 and 4. But one thing we should note is that they have a difference of 1. So let's take it that linear expansivity of P is equal to 2 and the linear expansivity of Q is equal to 3. Then we have to find the ratio of their increase in length. Let's take that original length of P is equal to 3 and the original length of Q is equal to 4. Bringing our formula, which is the linear expansivity of P equal to the change in length of P over its original length and then the change in temperature. Then we have the linear expansivity of Q equals to the change in length of Q over original length and the change in temperature. Now in this question, we were told that they were heated through the same temperature, meaning that this temperature cancels out because they are the same. Here we have the change in length. Here we have the change in length for P and the change in length for Q. Now let us put in our values. The linear expansivity of P is 2, the change in length of P is unknown, and the original length from here of P is 3. And then we have the linear expansivity of Q is 3, the change in length of Q, that is unknown, and then the original length of Q is 4. Now let us take a ratio whereby we say 2 divided by 3. 2 divided by 3, that is, we are dividing the first parameter by the second parameter, right? So 2 divided by 3 equal to change in length of P over 3 divided by change in length of Q over 4. We have 2 over 3 equal to change in length of P over 3 multiplied by 4 over change in length of Q. So with this, let's change in length of P be here. Let's the numbers. Okay, so we have 2 over 3 equal to 4 change in length of P over 3 change in length of Q. Let this 3 only come here and let this 4 come here. So we have 2 times 3 over 4 times 3 is equal to change in length of P over change in length of Q. 2 cancels 2, we have 2 here, then 3 cancels 3. So we are left with 1 over 2 is equal to the ratio of the change in length of P to the change in length of Q. And so the answer to this question, that is the ratio of the increase in length. So the increase in length of P to Q is 1:2. That is our final answer. Here comes a question that says a metal of volume 40 cm cubed is heated from 30 degrees Celsius to 90 degrees Celsius. The increase in volume is dash if the linear expansivity of the metal equals to 2.0 times 10 to the power minus 5. Alright, so we have that the metal of volume 40 cm cubed. So the original volume is 40 cm cubed. And then we're told that it was heated from 30 degrees Celsius. So meaning that the original temperature is what? 30 degrees Celsius. And then the final temperature is 90 degrees Celsius. And we're told that the linear expansivity of the metal is 2.0 times 10 raised to the power minus 5 per Kelvin. We have to look for the change in volume. From the equation, we are dealing with cubic expansivity. And we are aware that cubic expansivity equal to 3 alpha. That is 3 times linear expansivity. That is 3 times 2 times 10 raised to the power minus 5. So we are left with 6 times 10 raised to the power minus 5 per Kelvin as the cubic expansivity. Now we have that the cubic expansivity is equal to the change in volume over its original volume times the change in the temperature. So we have 6 times 10 raised to the power minus 5 equal to the change in volume, which is what we are looking for. Its original volume is 40 multiplied by the change in temperature, that is 90 minus 30. So we have the change in volume equal to 6.0 times 10 raised to the power minus 5 times 40. And so we are using this to multiply this. And so we have 6.0, so multiply by 90 minus 30, which gives us 60. So when we multiply all this through, we find that our change in volume is equal to 14400 times 10 to the power of minus 5. And that is the same thing as saying 0. So we have minus 5, so we move the decimal 1, 2, 3, 4, 5. So the decimal will be here. That will be 0.144 centimeter cubed. Question says metal rods of length 20 meter each are laid end to end to form a bridge at 25 degrees Celsius. What gap will be provided between consecutive rails for the bridge to withstand 75 degrees Celsius? Taking the linear expansivity of the metal to be 2.0 times 10 raised power minus 5 per Kelvin. Here we have two metals laid end to end, and like we said in the application of linear expansivity, in making a rail it's good to have space, because during the hot period the metal tend to expand, and so the space is for expansion of the rod. Now we're told that the original length of the rod, that is L1, is 20 meter, and at an original temperature of 25 degrees Celsius. Now the final temperature at 75 degrees Celsius, and we're given the linear expansivity to be 2.0 times 10 to the power of minus 5 per Kelvin. We are to calculate the space. The space we are looking for is the change in length. So this is simple. We're having that change in length, the linear expansivity equal to the change in length over its original length times the change in temperature. The linear expansivity is 2 times 10 raised per minus 5 equal to the change in length, which is unknown, and then the initial length, which is 20, times the change in temperature, that is T2 minus T1, which gives us 50. So the change in length equal to 2 times 10 raised per minus 5 times 20 times 50 equal to, so that's 20 times 50, that's 1000 times 2, that's 2000 times 10 raised per minus 5. So when we bring this minus 5 here, we move it 1, 2, 3, 4, 5. All right, so we have a 0 here, so we have 0.02 meter as the change in length. This next question says a blacksmith heated a metal whose cubic expansivity is 6.3 times 10 raised per minus 6 per Kelvin. The area expansivity is what? We have to look for the area expansivity. Now earlier on we established the relationship between cubic expansivity and area expansivity, that 3 times area expansivity equal to 2 times cubic expansivity. And so we have 3 times beta, which is unknown, equal to 2 times 6.3 times 10 raised per minus 6. So we have the area expansivity equal to 2 times 6.3 times 10 raised per minus 6 over 2. That is, we bring this 3 from here to this place. So we have 3 here, 2.1. So we have 2 multiplied by 2.1, that's 4.2 times 10 raised per minus 6 per Kelvin as the area expansivity of the metal. Next question says convert 45 degrees Celsius to Fahrenheit. So once we convert 45 degrees Celsius to degree Fahrenheit, important of all is to remember the formula, which says temperature in Celsius over 100 is equal to temperature in Fahrenheit minus 32 over 180. We substitute the values in, we have TF minus 32 over 180. So we cross multiply and we have 45 multiply 180 equal to 100 multiplies all this. So we have 100 into bracket T temperature in Fahrenheit minus 32. We have 45 times 180, that is 8100 equal to temperature in Fahrenheit times 100 minus 3200. We collect like terms, that's 8100 plus 3200 equal to 100 temperature in Fahrenheit. When we add this, we have 11300 equal to 100 temperature in Fahrenheit. So divide both sides by 100, we have temperature in Fahrenheit to be 113 degrees Fahrenheit. Next question says the lower fixed point corresponds to a length of 20 millimeter on the stem of a thermometer, while the upper fixed point corresponds to 160 millimeter. The temperature corresponding to a length of 48 millimeter is what? Here we are talking about a thermometer which is graduated. We have the lower fixed point. In the question, we're not given the value of the lower fixed point, but we will take it for a typical thermometer that it is 0 degrees Celsius and the upper fixed point to be 100 degrees Celsius. Then we're told that the lower fixed point correlates with 20 millimeter, as that is the point where it is. That is the point where the lower fixed point is, and then the upper fixed point correlates with 160 millimeter. We have to find the temperature corresponding to a length of 48 millimeter. So what will be the temperature? So the way to carry out this is you could give these points separate values, like having this as A, B, and C. Have this place as D, E, and F. But then you could do it straightforward without naming all this. Alright, so naming this, we have it that the distance between B and A that's B minus A, divided by the distance between C and A, that will be C minus A. That's the temperature difference. Then it's equal to the difference between the distance E minus D over F minus D. Our B here is unknown and A is 0 over C is 100 minus 0. Then E is 48 minus 20 over F, which is 160 minus D, which is 20. So when we subtract, we end up having x minus 0 to be x. 100 minus 0 is 100, equal to 48 minus 20, that's 28, over 160 minus 20 gives 40. So x equal to 100 times 28 over 140. And so we are left with x equal to 20. The temperature corresponding to 48 millimeter is 20 degrees Celsius. It says, what is the equivalent of 20 Kelvin in degrees Celsius, and what is the equivalent of minus 93 degrees Celsius in Kelvin? So let's bring our formula that says temperature in Kelvin equal to temperature in degrees Celsius plus 273. For the A part, we are giving our temperature in Kelvin, so that's 20 equal to temperature in Celsius plus 273. Bringing like terms together, we have 20 minus 273 equal to temperature in Celsius, and we are left with minus 253 degrees Celsius as our temperature in Celsius. So here is the answer. Then the B part is where we have minus 93 degrees Celsius. We have our T, temperature in Kelvin, equal to temperature in Celsius plus 273. We have to look for temperature in Kelvin, then temperature in Celsius is minus 93 plus 273. And so we'll be left with minus 93 plus 273. That is 180 Kelvin as the temperature in Kelvin. Question says, calculate the length which corresponds to a temperature of 20 degrees Celsius if the ice and steam points of an ungraduated thermometer are 400 millimeter apart. So we have a temperature scale where the ice point is 0 degrees Celsius and the steam point is 100 degrees Celsius. And we're told that it is ungraduated. The distance between the 0 degrees Celsius and 100 degrees Celsius is 400 millimeter apart. We're not given the value of 0 degrees Celsius, neither were we given that of the steam point. But we have to calculate the part which corresponds to 20 degrees Celsius. So we would follow it just as we've done. So what is going to be the corresponding length over here? So we could have it as A, B, C, D, E, F. So we have the distance from here to here, which is 20 over the distance from here to here, or the temperature difference from here to here, which is 20 over the temperature difference from here to here, which is 100, equal to the distance from here to here, x, is unknown, and the distance from here to here, which is 400. Making x the subject, we have x equal to 20 times 400 over 100. And so we are left with 20 times 4, that is 80. So 80 millimeter is the corresponding length of the temperature 20 degrees Celsius on this thermometer. The question that says, if the electrical resistance from a platinum at 0 degrees Celsius is 10.50 ohms and 12.80 ohms at 100 degrees Celsius, calculate the temperature when the resistance is 11.75 ohms, assuming that the change in the electrical resistance of the conductor is proportional to the change in the temperature. So no much work here, just to have a scale similar to other types of thermometer. We're told that at 0 degrees Celsius we have 10.50 ohms, and at 100 degrees Celsius we have 12.80 ohms. We have to find its corresponding temperature when the resistance is 11.75 ohms. And we are told that they are proportional, so that means we could easily find it such that the distance between the temperature here is x, that's x minus 0, and then the distance in the temperature here is 100 minus 0, which is 100. And then the distance between here and here, that will be 11.75 minus 10.50 over then the distance from here to here, which is 12.80 minus 10.50. And so we'll have x over 100 equal to 1.25 over 2.3. So x is 100 times 1.25 over 2.3, and that will leave us with 54.35 degrees Celsius as its corresponding temperature. The coefficient of linear expansivity of a metal is 0.000019 per Kelvin. What will the area of 400 millimeter square become if its temperature is raised by 10 Kelvin? We're told that the coefficient of linear expansivity of the metal is 0.000019 per Kelvin. We have to find the area, so meaning that we have an original area of 400 millimeter squared. We have to find the increased area if we have a change in temperature of 10 Kelvin. So to solve this, we have our formula that area expansivity is equal to the change in area over the original area, then multiplied by the change in the temperature. Alright, now we also know that we're not given the area expansivity, but we know that area expansivity is 2 multiplied by linear expansivity. And so we have it at 2 multiplied by 0.000019. That will give 0.000038 per Kelvin. So we have our area expansivity. So we replace that into this equation. So 0.000038 is equal to the change in area over our original area is 400 multiplied by the temperature change, which is 10. So we have it that our change in area is equal to 0. As this multiplied by 400 times 10, and that will leave us with 0.152 millimeter square. So here is the change in area. Now we should take note that change in area is equal to A2 minus A1, and we are looking for A2. So we know our change in area, we know our original area, and so the change in area, which is this, is equal to the new area multiplied by the original area, which is 400. Making A2 the subject, we have 400 plus 0.15, so we have 400.152 millimeter squared as the new area.